Hello, everybody. Can you hear me, right? Mi sentono, no? Okay. Okay. So today we're gonna speak a little bit about electric propulsion and why do we use electric propulsion instead of chemical rockets. And we will focus also in particular about Helicon plasma thrusters, which is a new concept of electric propulsion systems, a very exciting one. Okay. But first, we have to answer to one question. Why we use electric propulsion systems instead of chemical rockets? Well, let's see firstly some difference between the classical chemical rockets and the electric propulsion systems. So the chemical rockets, as you can see, we normally make some sort of combustion, and then we expand the byproduct gases through a nozzle. So it's a physical expansion of some highly enthalpic gas, let's say. When we talk about electric propulsion systems, instead, we accelerate the propellant by means of electromagnetic body forces. So body forces, for example, electrical fields, magnetic fields, it's not an exchange of surface forces like in the physical expansion. Okay. So in chemical rockets, what do we have? We normally use them for impulsive maneuvers, okay? So we have specific impulses up to 450 seconds. We will see that this is not high enough for many missions. That the exhaust velocity of a chemical rocket is limited, and in particular, sorry guys, we have a beer moment, so apologize for that. So I was saying that in chemical rockets, we have that the exhausted velocity when we have the expansion is limited. And is limited actually by some factors. The first of all is the chemical energy, which is stored in the chemical bonds. So we have the propellant. It makes some combustion inside the combustion chamber. And then which means that we are converting the chemical energy within the bonds in enthalpy that we can expand. But not all the chemical energy that is within these bonds is convertible. We have another limit in the tolerable heat transfer that the structure has to bear. So the expansion is physical. It means that we are exchanging surface forces between the gas and the walls of the nozzle. And so that, as we will see, that this is a very huge difference between chemical and electric propulsion system, where we use body forces. And so the fact that we are exchanging surface forces between the hot gases and the walls of the nozzle means that we have some constraint in terms of design when we design the rocket. When we design the rocket, we have to take in account that the nozzle is made by some material. It has to bear some heat and also some stresses. We have stresses, of course. We have the internal pressure, which varies with the expansion. We have some vibrations. And so we have to take in account of all of these factors. Third, we have a limit in the energy deposition of the chemical energy within the bonds, which can be deposited in some degree of freedom of the byproducts. So if we have a combustion reaction, okay, think about hydrogen and oxygen, the resulting are molecules, for example, H2O, water. Water has more degree of freedom, for example, with respect to atoms or H2, O2, for example, because we have a molecule which is made of 3 atoms. We have vibration degree of freedoms other than rotation degree of freedom and translational. And so we have that the energy that is exchanged during the combustion can be deposited also in some of these degrees of freedom, which are not the translational one, which are the ones that are convertible through the expansion. And so we cannot use them. We are just wasting this energy. And of course, we have also radiation losses. The gas has a very high temperature and exchanges with the environment, the energy by radiation, by radiational heat. And that's all energy that we are losing. So those are more or less the limits of the chemical rocket. Let's see the electric thruster. Electric thruster produce a very low thrust. Okay. What does it mean, low thrust? It means that the thrust is low with respect to the local gravitational acceleration. And in fact, they are used for continuous maneuver, so they are not impulsive. The specific impulses that we can reach with electric thruster are very high. We will see why this concept is true and why this is a thing that we are attracted of. I mean, we are attracted of this thing that the electric thruster can develop a very high specific impulse. And as we said before, the exhaust velocity does not depend on the chemical reactions that, I mean, does not directly depend on the chemical reaction. They have some sort of influence. I will go through details later, but they depend mainly on the electromagnetic forces, body forces that we are applying on the propellant. Okay. And lastly, the attainable exhaust velocity is of course limited by the power that we have on board the spacecraft. So we will see, we will record some equations and we will see why. Okay, this thing seems to be paralyzed. So let's record some relations about propulsion performances. Thrust, as you should all know or remember, thrust is given by the mass flow times the exhaust velocity. Specific impulse. The specific impulse is the exhaust velocity divided by G0, which is the sea level acceleration constant. Sorry, guys. We have another fantastic beer moment. Ah, okay. So we can. Okay, beer moment ended. So let's continue. Exhaust power. The exhaust power, which is the kinetic power exhausted with the gases by the thruster, is proportional to the electric power that we input inside the thruster. And it is proportional by a constant, which is the efficiency of conversion of electric power to kinetic power. The efficiency of conversion is defined as you can see here. So it's the kinetic power. Actually, I forgot here that this should be m dot. Sorry for that, guys. So in the numerator, we have the kinetic power of the beam, which is exhausted by the thruster. And at the denominator, we have the input power that we provided to the propellant in order to accelerate. And of course, this should be equal to the kinetic power in output itself, plus all the losses. And the losses are, if you remember, are given by inefficiency due to due to the charged particles that can impinge to the walls, can impinge to the grids of the thruster. Power to thrust ratio, very important quantity. And as you can see, it is proportional to the specific impulse. And the most important equation of everything that we need for propulsion, for designing propulsion system, is the Tsiolkovsky equation. So the delta V increment that we need to provide to a spacecraft for a certain mission is proportional to mainly two things: the exhaust velocity of our thruster and the mass ratio. So when you design a rocket, you have to, when you are in the design phase and you have to decide which propulsion system I have to choose, you have to think about two things: the technology, which means the exhaust velocity. I'm going to use solid propellant rockets. I'm going to use liquid propellant rockets, electric propulsion. So that means what exhaust velocity or specific impulse I want to use. And the second thing I have to take in account is the mass ratio. So the logarithm of m0 over mb. m0, I recall, is the total overall mass of the propulsion system. So with the tank age, with the fuel, with the payload and everything. And mb is the total mass minus the propellant mass. The propellant mass that we are exhausting with our propulsion system. And so you can see that as a propulsion designers, we can work in two directions. Let's plot this equation and see. We have in the x-axis the mass ratio. Okay, so go back, m0 over mb basically. And in the y-axis, we have the delta V increment that I can reach with that propulsion system. And we have many curves for many different technologies, as you can see plotted here. I plotted this red line, which is the requirement of a mission from low Earth orbit to Jupiter. So this is the delta V that we need in order to design a rocket that has to go from low Earth orbit to Jupiter. What kind of propulsion system I should use? Well, let's see. The first one, the solid line, is the Saturn V engine. It has a specific impulse of 3 kilometers per second, which means 300 seconds in MKS units. We can see that in order to satisfy the demand of the delta V, I have to go with an insanely high mass ratio. What does that mean? It means that, okay, maybe if I go asymptotically here, I can reach Jupiter. But I'm gonna bring to Jupiter a notebook maybe, not a 1-ton payload or astronauts. So it means that the payload mass that is available, it's so low. And so we are not interested in this technology. Then we have the space shuttle, which is another liquid propellant rocket. Same technology, a little bit more, with more performance, 450 seconds of performance, specific impulse. We see that at a certain point, eventually, we're gonna satisfy the demand, but still with a very high mass ratio. It means that I'm spending a lot to bring so low mass. Not interested in this, actually. Let's see some electric propulsion systems. For example, the Vasimir. The Vasimir, it's Helicon plasma thruster, a sort of Helicon plasma thruster, developed in cooperation with NASA at the moment, never flown. I think it is TRL 7, 8 or something like that. But as you can see, with a relatively low mass ratio, we can satisfy the demand. And we can reach Jupiter, carrying with us a lot of mass. And so we start seeing that where is the advantage of electric propulsion system? The advantage of electric propulsion system lies in the specific impulse, the exhaust velocity. The higher, the better to bring more mass. So let's recap. For chemical rockets, exhaust velocity or specific impulse, we have seen that depends on the heat released during the combustion, and of course also inversely by the mass of the byproducts. So it's limited in the chemical energy of the combustion. Whereas the exhaust velocity and thus the specific impulse of electric propellant rockets are limited in power. The more power I give, the more specific impulse I can obtain, even infinity. If I have power, I can go. So, what type of electric propulsion systems are present today, nowadays? We have mainly three electric propulsion systems. We have the electrothermal propulsion, like the arc jet, resistojet. What is the main characteristic of this propulsion system, sorry? It is that you use some propellant, you heat it up with electric energy. So with the arc or with resistance, you heat hydrogen or other gases, and then you expand them through a classical nozzle. So those are the electrothermal propulsion. Then we have the electrostatic propulsion system, and you can see that the specific impulse starts becoming very high. And the peculiarity of electrostatic propulsion system is that we accelerate the propellant through electrostatic body forces. So we apply an electric field, a certain voltage drop, basically, and then we accelerate the charged particles that are produced in an ionization chamber. Example of these are the ion engine, the grid and ion engines, the Hall effect engines, and the FEEP, field emission electric thruster. Another concept are the electromagnetic propulsion systems, like the MPD or the Helicon plasma thruster. Electromagnetic propulsion systems use both electrostatic and magnetic fields in order to accelerate the plasma, for example, through the Lorentz force. So you can see here an example of an ion engine that lies in this category, electrostatic propulsion, and here you can see, let's iconize this. Okay, an example of electromagnetic propulsion system, an Helicon plasma thruster where there is some plasma, there are magnets, there is a magnetic nozzle, and this is an example of electromagnetic propulsion system. We will go through the electromagnetic propulsion system more detail later. Okay, I think there is some problem by clicking. Okay, but we said, let's see first another very important concept. We said that when we want to design our rocket, we are interested in the technology, and so electric propulsion system that can provide specific impulse, a very high specific impulse. Can we just go with a very high specific impulse as just we want? Or there are certain limits or certain conditions that we have to respect and take in account? Well, of course, the answer to this obvious question is no. We cannot just go with an infinite specific impulse. We have to respect some condition. Let's consider, for example, to have some mission, okay, that's of time delta t. And you have to provide a certain velocity increment with a certain propulsion system at a constant thrust, F. Okay, let's see now, our goal now is to see the total mass that we are going to waste during this mission and the mass of the power plant that we need in order to complete this mission. And we will see, we will draw some conclusions, some conclusion about what we have to do when we design an electric propulsion system. So let's see the mass delta m, the total mass delta m that we are wasting during the mission. This is, of course, m dot times delta t. Okay. Let's multiply and divide by UE, and we get that this is F times delta T over UE. UE, the exhaust velocity, is the specific impulse, and all this math is just to say that the exhausted mass during the mission is inversely proportional to the specific impulse. Okay, take this in account. The total mass of the mission, exhausted during the mission, is inversely proportional to the specific impulse. Let's take in account now that to provide that specific impulse, we need some power. We have seen that specific power is proportional to specific impulse. How do we produce power in our propulsion system? We produce it with some power plant in the spacecraft, right? Whether it is solar arrays or nuclear power plants like RTG, radioisotope, we need some power plant. That power plant has some mass, some weight, okay? And the weight of the power plant, it is quite reasonable to assume that will scale up with the power itself that the power plant is producing. So if we are producing a certain power P, the mass of the power plant will be linear with P according to a certain coefficient alpha. So there is a linear proportionality between the power produced by the power plant and the weight of the power plant. Proportional to this alpha coefficient, which depends on the technology. You are using solar arrays, alpha maybe it's quite high. You are using radioisotope, maybe alpha it's a little bit lower. Because you are developing, because radioisotope, with respect to solar array, I have to check this. I don't know, don't remember. If it produces a lot of power, and the mass is and the weight of the power plant is quite compact, then alpha is small. But the main thing that you have to take in account is that the mass of the power plant is proportional linearly with the power produced. And again, this means that it's proportional linearly to the specific impulse. And so we have seen that during the mission, the exhausted mass of my propulsion system was inversely proportional to the specific impulse, but the mass of the power plant that is producing that power for generating that specific impulse is actually linear with the specific impulse, which means that we have this type of behavior of my total mass, which is not my payload mass, okay? This is mass that is not useful. It is not something that I am bringing as a payload. It is something that I'm bringing in order to arrive there, basically. And we can see that there is actually an optimum, because our goal is to minimize the mass of the power plant and the propellant that we are using in order to maximize the mass of the payload that we are bringing to our destination. It means then that there is an optimal specific impulse, and we can easily find it via derivation, imposing equal to 0, and then we find that the optimal specific impulse, it is actually not depending on the thrust of the mission. It depends on eta, delta t, and alpha. Eta, I recall, is the efficiency of conversion of electric power to kinetic power. So the higher the efficiency, the better. Delta t is the time needed to complete the mission. And alpha is the linear constant that relates the power produced by a certain power plant and its weight. And so we, of course, want the low alpha possible. So we are limited in this sense. We have to choose an optimum specific impulse in order to maximize our mass payload mass ratio. Maybe in the future when there will be fusion nuclear reactors, this alpha will become very low, and this will be helpful for space propulsion. Okay, let's see now a very interesting concept of electric propulsion system. This guy here is called Helicon plasma thruster. Actually, the marketing guys calls it magnetically enhanced plasma thruster. Anyway, it's a plasma thruster. It works with plasma. But what is it, this plasma thruster? This is a small device that is basically intended to propel small satellites. It can work also with big satellites. There are some scale up, like the Vazimir, but this is intended for small satellites. It is a very interesting concept, and it has some differences with the classical electric propulsion system that you have seen. First one, it works with ambipolar plasma. What does it mean, ambipolar plasma? It means that it is a gas made of ions, positive ions, negative ions could be also as well, electrons, and neutral particles. So if you remember the ion engines that you studied in the propulsion course, you had an ion gas, okay, a positive ion gas. In this case, we have both positive ions, negative ions, and electrons at the same time, homogeneously mixed as our working fluid. Okay. We use electromagnetic body forces in order to accelerate this plasma. How? We use the magnetic nozzle effect. The magnetic nozzle is basically these diverging lines of the magnetic field. It's called magnetic nozzle. We will go through that in a few moments. But first, let's see how the plasma is produced. So we have some gas in the tank. Can be argon, can be xenon, can be krypton, can be actually a lot of typology of gases. In fact, a very good thing of this Helicon plasma thruster is the versatility in the propellant selection. So we have some gas. We just let the gas enter inside this dielectric tube. So it's a dielectric. It's a cylinder made of boron nitride or any other dielectric material. The gas enters here, and then we power an antenna, which is this one that you see here. The antenna, it's just a copper ring. Actually, can have many shapes, but let's just take a copper ring, and we power it with AC power at a certain frequency. We just go there with our plus and minus and power it with a certain frequency. In Helicon plasma thruster, the frequency is 13 megahertz, but just to give you an idea of the range. And this antenna starts sending some electromagnetic impulses, some radiation. The radiation polarizes the free electrons present in the gas. I didn't say that the gas is released here at a very low pressure. Okay, when you release some gas at very low pressure, you have free electrons as well. In normal air here, like here, the free electrons are so low that are basically not existent. They are not present because they are so low in number. But when the pressure of the gas starts becoming so low, you have a certain amount of free electrons. You can polarize these electrons. And so the antenna starts sending some electromagnetic waves that polarizes these electrons. The electrons polarized by these waves becomes energetic and start moving around. And moving around, they collide, they impact with neutral particles. Okay? And as you maybe the master degree student has already seen that, the bachelor no, but when electrons impact neutral particles with enough energy, the neutral particle can free some other electrons. And it becomes an ion. And so you have an ionization event. And that's how the plasma is produced, actually. It's very simple. There is a magnetic field which is produced by these coils. These can be coils or permanent magnets. The purpose of these coils are to produce a certain type of magnetic field within the chamber of ionization and another type of magnetic field outside. Let me explain better this concept. Here, within the chamber of ionization, that is called also production stage, we have the plasma. The plasma, when is in contact with the walls, recombines and becomes neutral. And that's wasted energy. We don't want that. A way to prevent this is to confine the plasma with the magnetic field. Since the charged particles are confined by the magnetic lines, we can reduce the diffusion through the walls. And that's why here in the ionization chamber, we try to produce the most axial possible magnetic field lines, because this helps in reducing the diffusion of the plasma perpendicular to the magnetic field lines. It is through the wall. So this is just in order to enhance the production of the plasma itself, and so the efficiency of the overall system. But then, as you should know, by the second law of Maxwell that I'm sure that you know by heart, okay? The divergence of B is equal to 0, or there are no magnetic monopoles, okay? The field lines of a magnetic field always closes at infinity. So it starts diverging and eventually closes going at infinity. This is a result of the second law of Maxwell, divergence of B equal to 0. Why we need this? Because here we start having some divergent magnetic field lines. The divergent magnetic field lines means that we start having here radial components of the magnetic field. And since the plasma carries currents, because we have charged particles, it means currents, particles that move with a certain velocity, we can exploit the Lorentz force. And so we have some thrust. Okay, let's go, let's see the production stage. We have said that we introduce some neutral gas inside the electric tube. Sorry. Okay. We introduce the neutral gas inside the electric tube, and we start sending some electromagnetic waves. These electromagnetic waves at a certain frequency, a frequency that can excite and polarize the electrons, acts with a certain modes. You can see here depicted one of the modes. This is the electric field produced by the electron excited by the antenna. And this is called Helicon, Helicon modes. That's why the thruster is called Helicon plasma thruster. That's it. That's it. And so we said that we energized the free electrons that are present inside the neutral gas in order to produce ionization events like this, collisions between electrons and neutrals. When you produce an ionization event, the neutral frees an electrons, but that electrons becomes energetics as well, because it's energized by the antenna, and goes ionizing another neutral particle. And so it's a cascade, as you can see here. In fact, this is called Townsend avalanche, la valanga di Townsend. Let's see more in detail the acceleration stage. In the acceleration stage, we have the so-called magnetic nodule, as I was saying before. The plasma is made of charged particles, ions, positive ions, negative ions, and electrons. When charged particle moves, they produce currents, J, and currents with a radial component of the magnetic field. You can see the magnetic field diverging here, which means that a certain radial component becomes more important going axially, produce a Lorentz force. That's it. It's very simple. You have a Lorentz force, which produces part of our thrust, generated by the magnetic field that diverges and the currents present in the plasma. I put this as a comparison. This is the expansion through a physical nozzle that you all know. Why this is important? Because in a physical nozzle, the forces, the thrust, is generated by the exchange of surface forces. So the forces produced by the pressure of the fluid in contact with the walls, which means that a very low part of the flow interacts with the wall, generating this thrust. Here we have body forces. It means that all this volume here is acting in producing the force. So this is quite important. It means that we can influence more volume of material in order to generate the force that we need. Our universe. We are lucky enough to live in the 1% of the matter, of the condensed matter, which is not in the plasma state. The universe is made of interstellar plasma, stars, which are basically very hot plasma, hydrogen plasma, for example, in our sun, and a lot of cosmological formations, which are basically plasmas, and behave with the law of Maxwell. We are very lucky to live in the small part of the universe where the condensed matter is not in the plasma form. And so, yeah, we are lucky. But how can we define a plasma? There is a specific definition for characterizing a certain matter and saying, okay, this is a plasma. We define plasma when we have enough ion numbers in a certain volume of gas. If you take certain volume of gas here in our chamber, so air, you will find that there are many particles, many molecules of nitrogen, oxygen, argon, CO2, unfortunately, and other molecules as well. But we also have some ions in a very low amount, very extremely low amount. This is in our atmosphere, so with a certain temperature and with a certain total number of molecules. If we heat up the air in this room, the number of ions at a certain point, after a certain temperature, will break down exponentially, and the number of ions will be more than the number of neutral particles. And that's when you have a plasma, a fully ionized plasma. Of course, between normal gas and fully ionized plasma, there is a very huge intermediate range of what is normally called weakly ionized plasma or cold plasma, which is de facto also the working fluid that we use in our thrusters. In order to say what I said in a mathematical way, an Indian scientist, Saha, derived this beautiful formula, in which if you plug the numbers, for example, room temperature, sorry. So in our room, we have 10 to the 25 molecules per meter square. We have 300 Kelvin, let's say, maybe we have a little bit more right now. The ionization potential of nitrogen, which is the most common molecule present in air. And we see that the ratio between the number of ions and the number of neutrals here in air, in our room, it's 10 to the minus 122. There is no plasma, basically. So if you start heating up the air here, at a certain point, this will reverse completely. The number of ions will be so high that you, of course, cannot breathe. We will all die. Sorry for the dark, yeah, for the darkness. And we are in plasma state. Yeah. So the air will be made of ions, and we have a fully ionized plasma. I am done with this presentation. I'm going to switch to the, yep. Ragazzi, ditemi se vi sto annoiando perché purtroppo qua... Infatti nel tuo desktop vedo un po' di plasma. John? Okay. So we have seen the Helicon plasma thruster concept. Now, since for me you are not bored enough, I'm going to show you how in our research activities, so in laboratory, what we do. We try to model this Helicon plasma thruster with some physical models and some numerical methods as well. So we have seen the Helicon plasma thruster layout. Is this one. We have the classical production stage, the acceleration stage. And when we model it, we model separately the production stage and the acceleration stage. Let's see a nice video and see how it works. This nice guy is called Regulus, and this is produced by a company which is called T4I, Technology for Propulsion and Innovation, which is based in Padova, Italy. You can see here the ionization and the acceleration through magnetic nozzle, which is represented by these blue lines. There is, of course, a physical nozzle. Do you know why? Any guess why we still keep a physical nozzle as well? Well, because first of all, we are not dealing with a fully ionized plasma. We also have a neutral component of the plasma, of the gas, sorry, and the neutral component does not react to body forces. So we expand its enthalpy because it heats up when in contact with the plasma, and we expand it through a physical nozzle. Physical nozzle. So we can expand also the ions. The ions can be expanded as well. The electron, no, because the electrons are very small, and being so small, they are quite mobile. So it means that they just run around, and actually they react more to the magnetic field. I've heard that you like equations. Okay, don't hate me. Let's see, how do we model the plasma? You all have done, or at least I'm sure that you have seen some fluid dynamic equation. Navier-Stokes equation, for example. Don't worry, these equations are quite similar, actually. What are the Navier-Stokes equations? Are balances. We have balances of mass, balances of momentum, balances of energy. You've heard this countless times. We always deal with balances when we study fluids and the like. And the plasma, it can be treated as a fluid. The difference is that it is a fluid that reacts also to body forces like the electromagnetic ones. And so here we have, you can see this in the first equation. This is called the continuity equation. This is just the balance of mass. What is N? N is the number density. It is like the mass density that you all know, rho. It's like rho. But this is the number density. It means how many particles are present in a meter cube. If you multiply N by the mass of the particle, of the atom, you get rho, the density, the mass density. So this is just the normal continuity equation that you have seen countless times in fluid dynamics, aerodynamics, and so on. The only difference is that here we don't have that this is equal to 0, but this is equal to this R. What is R? R is a source sink term, because when we deal with plasma, we can create and lose particles. Okay? When we deal with normal fluid dynamics, with fluids, you don't create particles by nothing. So you just have balances, particles that enters and that leaves, but you don't have particles that in a certain control volume generates by itself. In plasma we do have, because we have the ionization events, and so you can have that at a certain point, in a certain point in space, some particles vanishes, and some particles of another species creates. And that's why we model this effect with source and sink terms. So this is just, this represents just that concept. So it's quite similar to the Navier-Stokes equation. Actually, the source of this equation is the same of the Navier-Stokes equation. The gamma that you see here, divergence of gamma, is just the flux of particles through a certain surface. N times U. Density times velocity, like in the Navier-Stokes equation. Okay. The only thing is that normally this term here, I think that they cannot see. Let's activate a pointer. Okay. So this point here, this term here. Normally, when you study aerodynamics, how do you solve this? How do you find this term? You find it by the momentum balance, the real Navier-Stokes equation. Okay. When you solve the Navier-Stokes equation, you solve for the velocity of a certain fluid, U. This gamma is the density times the velocity. The difference between the Navier-Stokes equation and the plasma equation is that we use a simplified version of the momentum equation, which would be the Navier-Stokes equation, which is this one. So the density, N times the velocity, it is given by this term, which just represents the electrostatic body force, and this term, which represents the pressure gradient force. The force due to the fact that in certain point in space, we have more pressure with respect to other points. And so there is a gradient, or better, we have more particles in a certain point with respect to another one. And due to collisions between these particles, the particle starts moving towards a zone of less dense population. The equation that you see here in the blue box is the energy equation. Don't worry about the terms. I realize that it is difficult to explain how the plasma works without giving you plasma physics course. But this equation is really similar to the energy equation that you already seen in the Navier-Stokes set of equations. This term is the internal energy. And this term here is the flow of internal energy plus the heat exchange. I'm sure that you are recognizing this term. This is the Fourier heat law. You should recognize it. You should recognize that. But don't worry. This term here represents the heating due to ohmic effect. So when you have a conductor and you make a current pass through the conductor, it heats. That's called ohmic work. Yeah?
Dissipation term.
Yes. And also in the energy balance, we have a source sink term. These are epsilon. Why I showed you this? In order to let you understand how we model the plasma. We have seen that the plasma is this fluid that we can energize with the antenna. So the antenna delivers some power to the plasma. That power is this expression. Don't worry about the expression in the term in itself. Just follow my reasoning. This is the source of energy in the plasma energy equation, which is given by the antenna. We also have some other sources, sink term actually, due to the fact that in the plasma we have also chemical reaction. When you have chemical reaction, a chemical reaction to happen can be exothermic or endothermic. In our case, the most of the chemical reaction requires energy. And so we have to consider this loss of energy in our equation when we model the plasma. And so this energy equation. It is needed because it can give us the power input provided by the antenna. So this is the drive of this set of equations, basically. How do we find the power input, if you are wondering? I'm sure that you are not wondering that, but if you are wondering, the remote case that if you are wondering, how do we find the power deposited by the antenna in the plasma? That's by solving the Maxwell equation between the antenna and the plasma itself. So Maxwell. So in principle, God said Maxwell equation, and then became light. Okay. This very ugly thing, I'm sure you are very interested actually on this. This is very ugly. This just represents the fact that when you have a magnetic field in a fluid, the constant, the coefficient of the equations, the coefficient of transport, like viscosity, like the heat conduction, and so on, are not scalars anymore. They become tensors. It means that they have a certain values in certain direction and other values in other direction because there is a magnetic field. So they are not isotropic, they become anisotropic. And that's why we have to deal also with these tensors. Yeah, magnetic field is ugly. Let's go through the chemistry. We have to take in account the chemistry, we said, when we model the plasma, because the chemistry is provide us with two information. First, how many species at a certain time are generated or are lost. And second, what is the amount of energy that is generated associated to this species or loss associated to the reaction that we are considering. And so we need these two information in order to perform our balances of energy, mass, and momentum. What are the type of reactions that can happen in a plasma? Well, you can imagine the plasma as a lot of particles, spherical particles, let's say, if we consider atomic plasmas. And in particular, we have neutral particles. Imagine, for example, argon, ions, and electrons. Okay, so we have spheres that collide between them. we can have that a neutral particle collides with an electron, and what happens? It happens that the neutral particle becomes ionized and becomes an ion. And so we have, the reaction will be neutral plus an electron will give me an ion plus 2 electrons. We can have many more types of reaction. For example, we can have also the excitation. If an electron impacts a neutral particle, but not with enough energy to ionize it, that energy can be deposited in the neutral particle and make it an excited particle. What is an excited particle? An excited particle is still neutral, is a still neutral particle, so it doesn't respond to electromagnetic fields, but has the electronic configuration of the excited electron perturbed. And in this whole situation, what is the meaningful information is that we have lost some energy. Energy that was useful for ionization, for example. And so we need to know the energy lost in the excitation process in order to account for inefficiencies. We have other type of collision, for example, radiative collision. You should know that when you have a charged particle that accelerates, it means that it changes direction, unless it accelerates straight. It naturally emits photons, radiation. So we have also this kind of reaction, charged particles that emit photons, light. Why this is important? Because that's energy wasted. It's energy that is wasted and could be used for ionization. You might wonder, but maybe you are not wondering that, that could this radiation energy be impact another neutral particle and ionize it? Yes, it can happen. It can happen, but the chances that would happen is so low, and the amount of ionization by radiation processes is so low that we neglect it. But yet, we take in account radiative effects. And also we have other type of collisions, for example, this charge reactive collision, where an ion impacts with a neutral, and the neutral exchange its outermost electron to the ion, which recombines, becomes a neutron, and the other neutron becomes an ion. So it's like two friends that exchanges money, but it's not money, it's electrons. Why it is important? Because that's a loss of energy. Let's go more through details about what we do in our research activity. We have studied many propellants. The most interesting are argon, krypton, and xenon. You can see some nice picture here of, if you didn't know, changing the type of propellant will change also the color of the beam outside the thruster. And it is not just an aesthetic thing, but we studied the reactions that happening with many propellants. The thing of argon, krypton, and xenon is that they are noble gases, and noble gases have a very similar structure, and so we can study them. We can model them with the same model, basically. Here at the right, you can see this. Very nice, indeed, it's nice. It's a nice scheme of how the excitation works of a single atom. In the center, you see GS. GS stands for ground state. Ground state basically means neutral atom. Okay, imagine an argon with the outermost shell full of electrons, and that's the ground state. When you impact it, you give it energy. One electron can go to other orbitals outside the outermost shell. The two main orbitals that we take in account are the 1s and the 2p. This nomenclature is the electronic configuration nomenclature that you have studied in chemistry, maybe. So I'm sure that you don't remember it. I mean, I myself don't remember it. But the first excitation orbitals are these two. And they are also the most interesting one because the experimental, by experimental evidence, we have seen that these are the most populated. And so we model them taking account all these excited states, the 1s and the 2p. Between the states can be certain transition, could be collisional or radiative. What are the transition? The one that we have seen here before. So imagine a neutral atom can impact with an electron, and that neutral atom can become an 1s5 excited atom, for example. It is still a neutral atom. It is not an ion because it still has its all the electrons, but one electron is in a perturbed configuration. It's in another orbital. In another orbital, which requires some energy. Because I recall between orbitals, there are energy gap, I recall. What can happen is that this excited atom, if it impinges another electron, can either be ionized or be excited to another higher level, or it can happen that it releases the energy to the electrons, and the outermost electron goes back to the ground, to the outermost shell of the argon, for example, and so it becomes again a ground state atom. That's called the excitation. Okay. Another thing that happens a lot is that when you have excited atoms, there are certain type of excited state which are called resonant, that as soon as they are generated, their configuration is unstable for quantum mechanical reasons that I don't know. And the effect that happens is they start releasing photons. So they release their energy by photons in order to go back to a stable level. And that's called the radiative decay. And it is represented by these lines. Anyway, this graph just represents all the possible transition between states of an atom. So let's go on. What we do in the propulsion lab, we play games a lot, but we also do something. And in particular, we develop numerical codes in order to study the plasma evolution inside the thruster. As we already seen, we have the production stage and the acceleration stage. We study the production stage with a certain code, and we study the acceleration state with another type of code. But let's see more in detail. We said before that we compute the power deposited by the antenna in the plasma by solving the Maxwell equation. You can see here an example. We solve the Maxwell equation with a finite element code, and we can compute the electric field inside the plasma and the current inside the antenna. This is the antenna, and this is the plasma column inside the source. Why we need to compute this? Because the electric field inside the plasma will give me the power deposited into the plasma. The current inside the antenna will give me some useful information in order to design the power supply of the antenna, which is a monte, come si dice, a monte? Which is behind the antenna. The plasma inside the source is solved by solving the equations that I showed you before, these ones. Yeah, this is the time for equations, right? And so we can compute, we can predict the plasma profiles. temperature and density and pressure. We need these profiles in order to compute later the acceleration stage, and so the thrust and so on. Here I reported a comparison with experimental measures that we did, and our code our code depicts quite well the results that we have measured. There are some differences in the peak of the order of 25%, 25-30%. It might seem a lot. It is not a lot in the plasma field. Actually, it is good. You wonder why? Because when you measure the plasma profile inside a plasma reactor, you have to insert some physical probes. But the plasma is hot. The probes melts. And so they don't work well. And so the data that we get often are not reliable. And in fact, that's why we have these very high uncertainty bands. The acceleration. We studied acceleration with a methodology which is called particle in cell. Anyone heard about particle in cell? Never, ever? Particle in cell, it's very simple. Basically, you consider the plasma as particles, as you can see here. It is not an Eulerian approach, it's a Lagrangian approach. You consider particles. So you just solve F equal m times A. Very easy. The particles themselves are not the real particles. You cannot solve 10 to the 25 molecules. It's too much. You consider macroparticles. So each macroparticle virtually means that you are studying a lot of particles that behave in the same way. So a macroparticle can represent up to 10 to the 6 real particle, for example. And so we study this macroparticle and we push them in time with the forces that are present in that moment. How do we compute the forces, the field forces? For that, we use the classical Eulerian approach. And the Eulerian approach is used to compute just the Maxwell equation. So we have this grid, which is needed just to compute E and B, electric field and magnetic field, that we need in order to know how to push these molecules in time with F equal m to A. F uguale m per A, ragazzi, proprio semplice, semplice. So that's the good thing of the particle in cell. It's simple, but gives a lot of insight on the physics, because you are considering real particles moving without further assumptions. But as you can imagine, it's very, very demanding from a computational point of view. So you need supercomputers in order to do meaningful simulation. We don't have supercomputers. We do what we can, and we try to solve the acceleration stage as well. And as you can see from this graph, which is basically a comparison with experimental measures, we are not that bad because we are within the uncertainty band. And so that's why, that's how we basically model the plasma. It is a very complex subject. I'm really sorry that I had to go through this equation, but it is very difficult to explain how the plasma works without giving you some plasma physics, let's say, elements. Anyway, I am sure that the equations didn't scare you a lot, and you are all interested in working in the plasma field, and especially electric propulsion field. Yee. Any question? Yeah. Which one? Yeah. Okay, the question is, if I could explain this diagram. Okay. The yellow line, the yellow points. Yeah. This one. Ah, okay. This is the electron density profile, and this is the electron temperature profile of the plasma in the acceleration region. You can see here, when I'm pointing, this is the source, the production stage. This is not computed. This is the result of another computation, particular this computation. And this is the result of the particle in cell. Actually, it is an interpolation profile, actually, because the particle in cell, it's a Lagrangian, and this is an interpolation. And this gives us the density. This is the number density, but you can imagine like the mass density. The mass density is the number density multiplied by the mass of the electron in this case. And this is the temperature. You can see, this is important because you can see that the majority of the electron is bounded, is confined by the magnetic lines. Okay, and at a certain point there is detachment. The detachment is where the thrust computation should stop. Okay, because the plasma, the plume, it's detached and it cannot exert forces anymore. The point where the detachment happens, actually, in plasma physics, it's still a matter of discussion. It's a mystery. Many people have many theories. Nobody knows actually what they are saying. We just compute it numerically and hopefully try to understand something. Temperature is useful as well because it tells us, for example, here you can see that there is a lot of particles, and these particles have a certain energy. The energy, the total energy is bounded. You can imagine the distribution of energy for each particle to be like a Gaussian, okay? Like a Gaussian bell. Many particles we have low energy, and the tails of the Gaussian, so some particles, very low particles in amount, will have a very high energy or temperature. And in fact, these are the very low amount of electrons that manage to escape the magnetic tapping. Yeah. Welcome. Other questions? Go ahead.
So talking about Helicon plasma thrusters, in the production stage, we want an horizontal magnetic field, right? Production stage, we want an horizontal magnetic field.
Yes.
While in the acceleration one, radial. Yeah. Do these requirements go together, or so? How do you make it like as horizontal as possible in the production stage and as radial as possible in the acceleration one?
That's a good question. Magnetic field topology optimization is very important. Yeah, we need in the source the magnetic field to be as most axial as possible. But we also have to deal with practical designs, and so we cannot bring so many magnets in order to have the perfect magnetic topology. And so what we do is we choose some configurations like this one. Let me go to a clear picture, like this one. So 3 magnets put in this configuration. This is called a Maxwell configuration, which is well known to produce a almost perfectly axial magnetic line here. But after this region, for the second law of Maxwell, it will diverge and it will do a magnetic nodule. Is the magnetic nodule the best topology that I need? Depends on this configuration. It is not the optimal one, but we can accept it because we cannot put, because in order to have the best topology here for the detachment, we should put another magnetic coil, maybe here. And this means weight, mass. Or if it is not a permanent magnet and it is an electromagnetic coil, it means also more power that I have to provide, that spacecraft has to provide. And so we accept, we do a trade-off, and actually, normally, what happens in reality, it's also that here, it's not perfectly axial, but we have to, since we use permanent magnets, we have some cusps here, some cuspidi, have some cusps. But the majority of the volume inside the cylinder, it's axial, and so it's good. So we accept to lose some plasma to be a little bit inefficient, but in order to optimize the overall topology of the it's a low power engine. It's 50 watt, 50. Yeah. È meno potente di una lampadina. But why? This is meant to power, to thrust small satellites, CubeSats. So that's why. Actually, this thruster, which is called the Regulus, is the son of another project, a 10 years ago project, which is called Strong. And it was a 1 kilowatt Helicon plasma thruster that never flown. It was a laboratory model, I think TRL5, something like that. So not even an engineering model. It was just laboratory model. A 1 kilowatt thruster that T4I managed to scale down and produce this 50 watt thruster. So you say 50 watt, it's nothing. Yeah, it's nothing. So you can thrust your small satellites, expending nothing in power. And so this is a very good thing when you have CubeSat that does not have very huge power generation capability, solar arrays or RTG and so on. And so that was the goal. I want to add something. When you think about electric propulsion system, you think about very high specific impulse. What do you think is the specific impulse of this concept? $3,000. The order of magnitude can be correct, could be correct. I said could because there is a reason, but any other guess? What could be the specific impulse of this concept? This particular thruster has a specific impulse of 600 slow. This is not the best electric propulsion system. I mean, from a performance point of view. And can you imagine why? Can you guess why? Sorry? No, 600 seconds. Sì. Quindi 6.000 metri secondo. È scarsino. Ah, ok. Okay. But why? No, it is not a matter of optimum specific impulse. 600 is the optimum specific impulse for this concept, let's say, for this specific design. When you have an ion engine, the specific impulse, which means the exhaust velocity, is produced by some acceleration, some electrostatic acceleration, right? So you provide energy in order to accelerate. Are we providing energy to accelerate here? This is a physics B O2 question. Yeah, but it's not because it is permanent. Also, even if it is, even if they are electromagnets, it is the same. So, but can you guess why? How are we accelerating here? Okay, sorry, it was in the other presentation. Never mind. How are we accelerating here? Lorentz force. Yep. Sorry, the natural? There is this, there is that term as well, but it is not that the reason. Okay. I give you a hint, guys. Don't think about the production stage, because this production stage can work also with an ion engine. You can produce ions not with the cathode and the anode, but with this Helicon production stage, and then eventually you collect the electrons, and so you have the ions, but then you have the grids. Here you don't have the grids, you have the magnetic nozzle. Do magnetic field exchanges energy? Does the magnetic field produce work? No, the answer is no. So here, what the magnetic field is doing is just converting the thermal energy of the plasma into kinetic energy through the Lorentz force. But when you have the Lorentz force, so a particle, a charged particle, which moves with a certain velocity around a magnetic field line, you are not exchanging work. You are not generating work. You are just converting the energy from a certain type to another type. So the permanent magnets can provide energy. Perpetual motion, no. So permanent magnets, what are doing? They are just converting the thermal energy, the heat, into translational energy, kinetic energy, through the Lorentz force. So that's why we are not accelerating actively, we are accelerating passively, just with the potentiality of the plasma itself, the thermal energy of the plasma. It is cheap, it is free, and that's why this thruster is of interest, but it's not it doesn't have performance like the ion engine. In the ion engine, you are actively accelerating the plasma, the ions, through electrostatic forces. You are exchanging energy with the capacitor. You are giving energy with a voltage drop. Doubts? Questions? Did you expect that? No. Okay, so guys, thank you for having me here.
Thank you, Nabil. It was a pleasure. And of course, if people are interested doing research on this topic, there are places, right?
Sure. If you guys are interested in doing thesis or internships, we have some topics that we want to work out. Just reach me at this mail, and we will discuss that. So don't hesitate. I'm sure that you are almost bored about the equations, but yeah, you are engineers.
We'll share the mail in the follow-up email. Thank you again, and see you for the next event. Bye.